Yeah, hi everyone. Good evening. Can you hear me?
Yes, ma'am.
Okay. So let's start the next command. Yeah. Is my screen is visible?
Yes, ma'am.
Okay. So as we have sorted the BAM file yesterday in the last session, now in this session we need to just remove the duplicates. And for that, we are going to use the command, like we are using the tool SAM tool. So the next is what? Conversion, sorry, to remove the duplicates using SAM tools RMDUP algorithm. So if I will just open the manual of SAM tools RMDUP, that is to remove the duplicates. So here we are having the option SAM tools RMDUP and enter. Once this is done, if you will see here that the command which is given in the usage, like how to use, this is what like a SAM tools, then RMDUP algorithm that is for the removing duplicates, then small s, capital S, then input sorted BAM file, and then output file, BAM file. So here what is this small s and capital S now? So small s that is for remove the duplicates for single end, and capital S it treats paired end as a single end. So it means like in the smallest option, it is tells the SAM tools RMDUP to consider only the sequence of reads when identifying the duplicates. Means in other words, it ignores any another characteristics of the reads and only look at the actual sequence of the DNA that the read represents. And the capital S, it is telling SAM tools RMDUP to perform the stricter duplicate removal if considered both the alignment start and end position of the read when identifying the duplicates. And this can be useful in the situation where sequencing errors or variations might cause a slight differences in the alignment position of identical sequence. Means in a simple word, if I will tell you, the hyphen small s is focuses only on the sequence, but capital S is a stricter option which is considering both the start and end position of the read in addition to their sequences. Means if we will just break down this small s, actually think like looking at only the words in the book without caring about anything else like the page number or author name. It's just interested in what words are saying. Just example I'm giving. And capital S, actually, this is being very picky about the duplicates. It's not only looks at the word in the book, but also checks exactly whether those two words are whether those words are on a correct page, or it wants to make sure that even if two passages looking similar, so they are actually in a same place or not. So everything it is just checking. So small s care about the words and capital S care about both the word and their position in the book. So that's totally up to you that you want to look for the sequence or other things. So as we want both, like we want to look only for the sequence, and we want to check from start to end also, and that's why we are using this both option. Okay, are you getting my point?
Yeah, ma'am.
You can tell me, I will repeat it maybe if it's not clear. Okay. So now let's prepare the command SAM tools RMDUP, then here you have to use small s, capital S. Then you have to give your input file. What is your input file? That is your sorted BAM file. And then you have to give your output file. So without any greater than symbol, here you have to give the RMDUP and then your id.bam file. This is your command. I'm just going to copy this, enter. Done. So how to see whether the duplicates are removed or not really? If you will see the file size of a sorted BAM, it's 130 MB, and if you will see the file size of the remove duplicated .bam, it's like 78 MB. It means the reads are removed, correct? So this is how we can remove the duplicates.
Done, ma'am.
Okay. So once this is done, now we need to do the variation calling. Okay, so what will be our step number 8? That is variation calling using GATK. Okay, but GATK, that is what genome analysis toolkit. But this GATK, it requires the input in the Picard tool format. You remember we have installed the Picard tool, right? So this GATK requires the input in a Picard tool format. So what are the input files basically we required for variation calling? First is what your BAM file, which is your remove duplicated BAM file, which is having a unique reads, and another you required your reference genome. So what you have to do, you have to first convert your reference genome into the Picard tool format, and then you need to convert your BAM file, unique BAM file, into the Picard tool format. Okay, so that's what our first step now here in the variation calling, that is conversion of reference genome into the Picard tools format. Okay, so now here if I will show you how to use this Picard tool, you can just go simply online. Here it is showing you the manual. And in this Picard tool, basically you need to use this option for now, create. You just have to search by Control F, create sequence dictionary. So you can see you just have to use this option, create sequence dictionary. It's for the reference sequence. So basically this tools, it is going to create a sequence dictionary file with the .dict extension from the reference sequence, which is provided in a FASTA format. So how to use the tool? Actually, this tool, if you install by the source code, it is having a jar file. So you have to run it like java-jar and the jar file. But as we have installed this Picard tool into the by the repository, so you don't need to use a jar file. You have to directly call the tool Picard-tools. Then you need to use the option create sequence dictionary, which is going to create the sequence dictionary. Then in as per the command here, in capital R, you need to provide your reference genome, and in capital O, you need to provide your output file. So capital R, our reference genome is chr17.fa FASTA, and in capital O, I'm giving the output chr17. You have to give the same name with the .dict extension. And this is what our command to convert a reference genome into the dictionary format. Can you try this?
Done, ma'am.
Okay. And we just
Yep.
need to run this command. Hmm. So if you will see this genome.dict file is created here, that is CHR17. If I just want to see or want to show you what kind of information is present into the uh, DICT file, it's just like a chromosome, the length, it's just some annotate ID and the file path. That's it. So this is what information you are getting in a DICT file. It's just a GATK required that. That's why we are converting it. But now our main task is to convert the unique BAM file into the Picard tool format. Conversion of unique BAM file into Picard tools format. So basically, this command line, when we are converting the Picard, whenever we are converting the BAM file into Picard tool, it is using some, it is going to replace some read groups actually there. So it is very commonly used a method. If I will just show you in the manual, first of all. So I'm just searching here, add or replace read group. So basically, this is what a command. Here it is going to be replace the read groups in the BAM file, and this tools enables user to replace all the read groups from the input file and assigning to the output BAM file. So whatever the read groups are there, it is just replacing from input file and assigning it to the output file. Okay, so this is what a command we are having, add or replace read groups. Then in hyphen I, we are providing the input file, and in hyphen O, sorry, in capital I, we are providing the input file, and in capital O, we are providing the output file. So first of all, let's prepare till here. I'm just going to call the tool Picard tools. Just see first of all, and then I will give you time to prepare. And here we are adding the option add or replace read groups. I'm showing you how to prepare the command. Then in capital I, we are providing our input file. What is our input file? This is remove duplicated BAM file. Capital O, we are providing the output file. So I'm giving the name as a Picard output.bam. Now, actually, it's a compulsory options you have to give, which is some read groups you have to assign as per mentioned in the command. So the first it is given, that is a RGID. RGID is nothing but what? This is a set of read group ID. So basically, these read groups which are used to group together the reads that were generated from the same sequencing run, or maybe they are having the same characters. Okay, means like we are saying up to now what is a read group. So read groups is nothing but a set of reads which is having either from the same sequencing run, or maybe they are having a similar characteristics. So RGID, if you want, like if you will see, uh, this is showing like not required, means like this is optional case. So if you don't give it, that's fine. But if you will see, there are some options which is given here. In front of those option, it is showing you required. So this option you must need to give in the command. And this is RGID is optional, so I'm not giving it for now. Next option we are having is the RGLB. RGLB is nothing but the read group library. So this RGLB or read group library, so basically this is representing the library from which the sequencing reads are generated. And libraries are nothing but what? It's a collection of the DNA fragments which are generated together. So maybe whoever has generated the library, if you know that person, if you know that biologist, you can just ask the name. Otherwise, we can just simply give the name, that is lib1 as per given here. Okay. Then the next option I'm giving here, that is a RGPL. RGPL is nothing but the read group platform. So this is indicating the sequencing platform which we use for the sequencing data. So in this case, it's a Illumina, but maybe if they have used something else like Solexa, Iron Torrent, Solid, so you just have to give the name according to it. Okay. In the SRA database, we are getting this idea, like what machine they used for the sequencing. Then next option here, that is a RGPU. RGPU is nothing but the read group platform unit. So actually, this read group platform unit is a set of read groups which is typically it's representing the specific flow cell lane or a sequencing unit within the sequencing platform. Means like uh, if I will just show you, I will just explain you about this RGPU. So it is representing us the specific flow cell length or a sequencing unit within the sequencing platform. So this RGPU value, it is depend upon how your sample is run. Maybe because there are different flow cells lane we are having. So maybe if it is running from specific lane, so you can give as a lane 1, lane 2, lane 3. Maybe if it is having some different sequencing runs, you can give run 1, run 2, run 3. Then there are specific machine identifiers also, machine 1, machine 2, or maybe any another unique identifier if you know about it. So you can just give that. Okay. But as of now, if you are not sure anything about it, just give the unit 1, because we are just running it from a specific unit of the machine. Okay, so that's why I'm just adding this as it is RGPU unit 1. And the last one here is the RGSM. RGSM is nothing but your read sample name, which is nothing but your sample ID you have to give. Read group sample name. So whatever our sample ID that we are providing, this is what ERR ID you can provide here. But this is what the required options I'm giving. But I want to give some another options as well here, just to understand this. Just give me a 1 second, I will show you. Hmm. So here also again we are doing the control F, and here you need to search for create index. Yes, so create hyphen index. So basically, this create index file is to this option we are giving just to create the index of the BAM file. Okay, so basically here this option is when we are okay. Before this option, I want to give one option which is sort orders. I want to give this option sort order. So basically, this is the optional option. If you want to give, you can give, otherwise, no need, which is going to sort the order of output. Means like whatever the output BAM file is going to create, it is going to just sort that. But as we have already sorted it, so that choice is yours. You want to give this option or not. But I don't want to take any risk, so that's why I'm giving this option. But sort or order based on what? So these are the options we have to give. Like you have to select. You want this unsorted or sort on the basis of query name, sort on the basis of coordinate, sort on the basis of duplicates or unknown. So what do you think, like on the basis of what we need to sort? Query name, coordinate, duplicate?
Coordinate, ma'am.
Hmm, right, coordinate, because we want it based on the coordinate. So I'm just giving this option sort order and based on the coordinate. So you should have to copy this as it is, because uh, this is a case sensitive. Then after this, I'm just searching one more thing, that is create index. So this create index, why? Because it is going to create the index of the BAM file. What will happen if it is going to create the index? The process will happen faster. And this option we must need to give if we are sorting the BAM file based on the coordinates. So whether to create a BAM index when writing a coordinate sorted BAM file. So whenever you are giving this option sort order based on the coordinate, you must need to give this option. There are two possible values of it, true and false. By default value is false. So if you want to create an index, then you have to mention this, otherwise no need. So as I want to create the index, because we are giving the option sort order based on the coordinate equals to true. So this is what the thing. And the last option I'm going to add here in the command is a validation stringency. So basically this validation stringency, it's related with the warnings and errors. So basically this validation stringency, if I will tell you about this, it's going to, there are three options in the validation stringency. Uh, Actually, this is an optional option. If you want to give, you can give, otherwise no need. So it is used for validating the genomic data, such as like a sequence file or our VCF file, which is going to create now in the variant calling format. So basically this option, it will going to ensure that your input data, it conforms to certain standards or certain expectations, such as a correct file format or a data integrity uh, or data conventions. So there are three options under it: strict, lenient, and silent. So this silent option means what? The silent option in a Picard tool, this option means the validation is skipped and errors or warnings won't be reported. Means like even if you are having an error in your VCF file or your BAM file, sorry, um, uh, or maybe there is a warning, it is not going to report that. It is going to proceed further without reporting the warnings and error. Strict means what? Actually, it enforces the strict validation rules. meaning it will flag any deviation from the expected format as errors. Means even if you will get a warning or even if you will get an error, if there is a warning also, it is going to stop the process. But the another option we are having, which is a lenient, so this is more relaxed option which is allowing some flexibility in the input data. Means like it is going to not consider the warning, but yeah, if any error is occurred, it will report that error. So see, generally, whenever we are getting any warning in our data, we are not considering it. But yeah, if we are getting an error, so at that time, yes, we are considering this. So the choice is completely up to you that what you want to use. But as per my opinion, right now we don't need to be worried about the warning. But yeah, if there is an error, we should need to report that. So that is why I'm giving this option, lenient option. So this is what a validation stringency I'm giving here is a lenient equals to lenient. So what I will do for now is just like I will make the command like this for you. Miss, like just a second. I will kept it for running once and then just to show you because you need to run this command. I'm just going to uh, make it in a two lines so that you can check it. So, first of all, is there any doubt in the command? Is it clear? Every option?
Yes, ma'am, it's clear.
Yeah. So, I will just make this command in a two lines so that it will be visible for you clearly. Yeah, you can see the command is running. So, yeah, please prepare the command. Make it in a one line, not like this. Okay.
Done, ma'am.
Okay. What about others?
Done, ma'am.
Okay. Okay. All right. So now once we have done with the file like conversion, so this created the BAM file Picard output dot BAM file. So obviously we are not able to read this because it's in a binary format and no need to read it anyhow. We just need to do the variation calling now. Variation calling using GATK Genome Analysis Toolkit. But GATK actually it's a tool which we have to download now because we didn't download it yet. So you just have to go with the GATK download. We need to download one specific version. So just see first of all and then download. Okay. So this is your genome analysis toolkit. You have to go with the download GATK. This is a 4.6 version, which is unstable actually. So we have to go with the latest version. You just have to go down 4.3. So this is what you need to download. I'm just going to copy the link address and I'm sharing it to you. You can just download this and put it into the DNSSEC folder. So actually it is going to download one zip file. I will show you like this. Yeah, so it is going to download this kind of zip file. You need to just right click and say extract here. So it is going to extract this GATK folder. Yeah, please download and tell me when it's done.
Yes, ma'am.
Ma'am, can you please open the notepad?
Yeah.
Ma'am, we download using the wget command only, right?
You can download it with the wget command as well.
Wget, yeah.
Otherwise, just directly download it and then paste it into the folder. Not an
Done, ma'am.
okay. So now how to prepare the command. So basically, if you will just see the manual like GATK. So in the GATK, we are using this haplotype caller algorithm. So you just have to use this GATK, then haplotype caller. Then in hyphen capital R, you have to provide your genome file. And in hyphen capital I, you need to provide your input file. And in hyphen capital O, you need to provide your output VCF file. So here, if you will just open the terminal from this GATK folder, which we have downloaded. So if you will do the ls, there are two GATK files we are having, like a local.jar and spark.jar. So we have to use this local.jar file. And as this is a jar file, so you have to run it like java-jar and the path of the jar file. So to get this path, you just have to type the pwd. And I'm just going to copy the path. So how to prepare the command? Java-jar. Otherwise, you can globalize it and directly call the GATK. The choice is yours. And then here, this is a folder path. Again, we are giving the slash, and you have to just call this file name. That's it. Then paste it over here. This is what your file path. Now we are giving the algorithm haplotype caller. So basically there are two algorithms are there. One is a haplotype caller, which is used to call the germline variations. And there is one another algorithm we are having in a GATK, which is a mutate2, which is used to call the somatic variations. So as of now, we are interested with the germline variations. We are giving this option haplotype caller. We are giving this algorithm haplotype caller. I will explain you how this haplotype caller will work. But first of all, let's just prepare the command for now. Then in hyphen capital R, we are giving our reference genome. But that reference genome, we have to give it into the dictionary format, right? Picard tool format. Then in hyphen I, which is our input file, that is the Picard output.bam file, which we have created in a previous system that we have to give. And then in hyphen capital O, we are giving the name to the output file GATK output dot VCF, which is a variant calling format. I will explain you how this haplotype caller will work, but this is how the command we need to prepare. And then you have to run it from the DNSSEC folder. Yeah. So if you will see, there is a one error we are having. It's not done because it is showing file not supported file type. Oh, sorry. I'm so sorry. Actually, we have to give the FASTA file only, not the dictionary file, I guess. Here we have to give the FASTA file only. Dictionary file is just for the tool which we should create in the folder. Ha. So whenever you are running, it is showing this CHR17. So this is what a FASTA index of the CHR17.fa does not exist. So this file, which is like chr17.fa.fai, this file, which is an indexed file of the 17th chromosome.fasta, it is not created. This is what a error we are getting. And if you will see, you are not having the file with the FAI extension. Rather than that, you have another files with some another extension. So what you have to do is, before this, you need to create the index. You need to create that FAI file. And for that, we are using the command FAI samtools FAI DX. So it is going to create the index of the FASTA file, and then you have to give this command chr17.fa. I just want to show you that error. That's why I didn't run this command previously. And we need to create the index first of all. Yeah, now if you will do the ls, this FAI file is created as per the given here, right? Now we have to run this command again, GATK command. Yeah, so it's running. You can just check the command here. Any doubt here?
So, ma'am, here in the command will not edit like instead of FA will write FAI.
No, but this file is not created now. Means like you need to create first the file FAI, and index file we are not giving in the command. It just tool required that in a folder. Okay.
Okay, ma'am.
Even if you want to give that FAI file here, but the file is not created yet. So that's why using FAIDX option, we created that FAI file, and that's how it will solve that error. Okay.
Yeah, ma'am.
Yeah. What about others? Is it clear? I hope you all are running the commands.
Ma'am, I have not understood this last full command.
Hmm?
Uh, the last command that you have given,
Which command?
last
GATK.
Java, yeah, haplotype caller.
What is the problem? Can you tell me?
And I have not understood which input file you have taken.
Input file we have taken is a Picard output.bam file, because from the aligned read only we need to, once the alignment is done, from that file only we need to find out by matching it with the reference genome, correct?
And where we have created this, I mean,
In the previous step, this step now, you can see we have converted the unique BAM file into Picard tool format. So we have given the input file as a remove duplicated BAM file and
okay,
output file as
okay,
a Picard.
okay. Yeah, yeah. I
Yeah.
think my name, RMDUP, I did not delete, so I could not find it.
Okay, okay. No, RMDUP you don't need to delete. It just you need to convert it into the Picard tool.
Yeah, but you changed the name, right? Picard, you put.
Yeah,
So
because
I put
as we
Picard
have.
also, this also. So yeah, that is okay.
Okay, okay.
Ma'am, could you know move the notepad?
Yes.
Done, ma'am.
Okay. What about others?
Yeah, done.
Yeah. Okay. Now, if I just want to explain you about this haplotype caller. So basically, this haplotype caller in the GATK, which is used for the variation calling, and is identifying the SNPs like a single nucleotide polymorphism and a small insertions, deletions, means what indels. But how it will work? Basically, it is working in a 6 steps. Okay. So the first is what local assembly. Like it just your for your theoretical knowledge, I'm telling this. Uh, so how it will work? So first of all, it is creating the local assembly. Means what? It is examining the small regions, means like a loci of the genome where potential variation might exist. It doesn't look at the entire genome, but just focuses on smaller chunks where the expected variations or a potential variations it can be present. Then next is what? within this regions, it is performing kind of puzzle solving. Means that's what we call it as a de novo assembly. Means imagine like if you have a puzzle pieces, like a reads of your DNA sequence, and that is going to be overlapped with each other. So this algorithm it is tries to piece them together and reconstruct the original sequence in that region. That is what a de novo assembly it will do. Then from this assembled pieces, so basically this haplotype caller it is going to be identify the different possible haplotypes, or you can say a sequence of a DNA that could explain the observed reads. So basically, this haplotype is essential a combination of genetic variants like SNPs or indels that tend to be inherit together. That's what we call it as a haplotype reconstruction. It is doing, and then for each haplotype, so this algorithm it is going to calculate the likelihood value that the observed reads would have come from particular sequence. And basically this is going to be involves the considering factors like quality, probability of errors and all. So this is what we call it as a likelihood calculation it is doing. Then based on these likelihoods, this haplotype callers determine which haplotypes are most likely to be correct and which variation, or you can say which variants, are supported by the data. It identifies the region where the strong evidence of variation compared to the reference genome. That's what we call it as a variation calling. And the last step means like a finally this algorithm it is assigns the genotype to each sample in the data set. Right now we are only having a one sample, so it is just assigning the genotype, which is indicating which variants are present in individual genome. So it determines whether each sample is a homozygous or a heterozygous. Like the variant which we are getting, it is a homozygous or a heterozygous, that it will determine, which we call it as a genotyping. So this is how it will work. Means like in a simple word, again, if I will tell you the haplotype caller algorithm, it is identify the genetic variations like SNPs and indels by assembling the short DNA sequence, which called read, into a longer or more complete sequence. Then it consider a different possible sequences that we call it as a haplotype, which is calculating the likelihood of each and determine which variations are present in the sample. And this approach enables accurate variant calling even in a complex genomic region. So this is how basically this haplotype caller algorithm will work. Okay. And ultimately it will give you the VCF file, which is a variant calling format file. But I will explain this VCF file because I need more than half hour maybe, or approximately half hour, to explain this VCF file in a detail. So we'll see this VCF file and the variation filtration in the next step. Are you getting my point?
Yeah, ma'am.
Hmm. Any doubt here? We still have some time. You can tell me if you have any question. Yeah. I
No,
hope
ma'am.
everyone's results are generated till the VCF file. If you have any error in the command, any doubt in the command, please tell me. Okay. So that's it about today. Rest of the things we'll discuss by tomorrow.
Okay, ma'am.
Yeah. Okay. All right then. Bye. Have a great day.
Thank you, ma'am.
You're welcome.